Maite, well, first I'm Anna, Sacristán, for those of you who don't know, and Maite. Maite is a biologist. She's a marine biologist. And, one of the things that happens is that biologists need research in that area, and it provides methods that assist in the decision-making that environmental scientists need to do. And so it's very important that environmental scientists and biologists and scientists understand the concepts of things like biological variability, which is one of the things we're talking about here. And it's just a basic concepts in language and method for the experimental design, data collection, analysis, to interpret and communicate scientific findings. But a very big problem is students' aversion towards learning statistics. There's this general mathophobia, using Patrick's word, and negativity not just to statistics, but in general to mathematics. And many of them say things like, we study biology because it doesn't have much mathematics. There's a failure of students to find meaning for the use of statistics. And when they do study statistics, there are many learning difficulties that come sometimes from previous statistics courses. And there's learning difficulties in probability, in ratio, proportion, statistical inference, and intrinsic variables. And one of the problems with the traditional courses, at least in Mexico, we were talking yesterday during the workshop that we have to be very specific what population we are talking about. So these are students in Mexico, the National University of Mexico, and some students also in Portugal, their career. And the teaching tends to focus on developmental and technical skills rather than understanding how to apply it. The software that is used tends to be black boxes or unfriendly and unreliable. So Statistica or Excel. And these are software that do not facilitate sometimes construction of drafts. And one big problem is also that this software that is used in courses is often commercial software that is not available to the students don't have access to it outside of class. So that's another problem. So Maite can talk a little bit about this if she wants later, if she has time. But what happened are several things. I gave her a lot of things in statistics education. And then, like half a year later, she called me up and she said, Anna, I love your logo activities. And I'm starting to do things with R programming and inspired by the logo, by logo. So I want to do things like that. So that was what drove us to do this, or mainly Maite and another colleague, Mascaró, in Portugal. So, so to have students engage in R programming in a constructionist approach, to give them tools for both statistics and also give them a tool that they could use for their own work and that they could understand. So give them tools that they could use to think and analyze their data. And we also wanted this constructionist approach, included this structured learning environment where especially Maite designed these activity sequences, but that also included collaborative work, types of models, different types of graphs, tables, etc., that students can analyze and relate to. And have these things. How many of you do not know what the R language is? You all know. Okay,
that's what we don't know.
Well, you know of it.
Ah.
Yeah. You don't know what
I know of it.
You know of it, yes. So everyone has heard of R. It characters, creates functions. It's free, which is very good, and it has this community, which is something I really like, where you can download the libraries and scripts and share your scripts and there are bloggers. So our project that we've been doing, 4 years ago. So it's a design research project, and we've designed art-based constructionist and collaborative programming activities, specifically for these environmental and biological science students. And it's been this iterative design as in design research. And it has this twofold purpose, again, I'm repeating myself, of providing tools for statistics and software. I have already said this. Okay. The activity sequences were structured through worksheets in our code, and they include examples, programming tasks, questions for reflection, comments, and commented solutions to previous activities. So they're all structured in R, in sort of in this type, like in the left-hand side. So everything is R. So far, Maite and my colleague have taught, I haven't taught these courses, have taught 14 courses to date, both mainly in Mexico, but some courses in Portugal through this iterative design, so being refined at each stage. So this is just a picture of some of the students and where Maite works. Coast of Mexico, the south, well, it's not so south, but the east of Mexico, on top of the Yucatan Peninsula. She actually works like literally from here to there is the sea, so it's very beautiful. She's on the beach. And so now she's going to explain a little bit, give an example of one of the activities that she did.
Okay, well, this is an activity for exploring the concept of randomness and related to variability. We want students to understand that a random process implies that values change in an unpredictable manner, that randomness is part of the natural phenomenon if it is treated as background noise, that we want students to develop meaning for the concept of the mean, its position and accuracy, and we want them to understand the effect of sample size on the estimation of population parameters. We want them to realize that stats is necessary to summarize information in the data, and that they can use graphics and numerical outputs to represent some of these features. Simultaneously, we want to introduce students into R programming and R coding, and we want to get to the statistical concepts through the actual programming. So activity number 2 is called frequency distribution, and it is particularly on continuous variables. Students are given the following context, a set of the total length of 100 C courses, and they are asked to carry out the following sequence of tasks. So this is like the type of little problem, contextual problem that they will receive. And this is important because they need to contextualize whatever activity they're going to do. So the first task will say, save the total length as a vector in R and name it shell. And they are expected to define the vector shell by typing in that kind of code. Then the second task would say something like, analyze the vector shell and describe observations on total length of C courses without any arithmetical operations on the data. And here we want students to confront the difficulty of summarizing information from a mere list of numbers. Then we ask them to create plots and graphs of the Chelen data by typing commands such as .chart Chel, for example, and compare the different charts. We give them hints to use our documentation, and we ask them to discuss the results amongst them with their partners. Students most of the time have been previously introduced to some of these commands, so they know the commands in order to provide to elaborate the graphs. Task number 4 asks them to use their previous knowledge on central tendency and dispersion parameters to explore the statistical nature of the Chelen example. And here we want them to get familiar to reading and understanding graphs. We want them to combine graphic information with numerical outputs. We want them to be able to identify values of the mean, to have a mean of such and such. What does it mean to have a standard deviation of such and such? We want them to be able to choose a graph based on information criteria that will serve a particular purpose. Task number 5 is build a new histogram of the Chilean sample using the following code. And here we give them 3 questions. So the first one says, what does the ab line do? And ab line is a code that produces a vertical line for the sample mean, which is a measure of location. Then we ask them to represent the range and the standard deviation for the sample by the same procedure. And here there is a strong conflict because the lines for the range and the standard deviation will not represent their value on the graph, because these are measures of dispersion and they are more related to the width of the figure rather than the location of the figure. And then we ask them to estimate, or they are able to estimate by an histogram and see if they can read beyond the graph and get information that is not readily presented in the graph. Task number 6 asks them to follow the code that was used to generate the vector representing the Chilean sample. And here they are asked to show if they can verify that the sample was randomly collected and which are the arguments that can be used to change the size of the sample in this code. Task 7 asks them to explore the relationship between the size of the sample and the parameters used to describe it statistically. And here they are expected to produce coding like the one that is shown here in the slide. And we want them to look at what S1, sample 1, sample 2 are, and what the means or the standard deviations or whatever parameter they have chosen would look like. What are the measures for these parameters? Tasks 8, 9, and 10 are all related to reflection on the relationship between sample size and the true population parameters. And we want them to use the plot function, for example, as a means to represent a trend, to be able to look at a trend and interpret one. So we wanted to observe students interacting with these tasks in a more precise way. And we wanted to do this in order to document their thinking in change and their understandings and difficulties while they were interacting with these elements, these programming elements. So Alexis and Iram and Isabel and Marcos are 4 volunteers, students. They are all from second year undergrad course in coastal zone management. So they are not biologists, they are supposed to be managers, or they will become managers. They have never studied statistics before they come to university, but they have had a recent 28-hour introduction to a course on frequency distributions and descriptors, statistical descriptors, during which they are introduced to some R commands for the very first time in their lives. So Alexis and Iram were generally above average, or could be identified as above average students, and Isabel and Marcos were average students. So task 2, that you recall that it was to provide a summary of observations in total length. And here Alexis and Iram discussed how to use R functions to order the vector and find the maximum and the minimum values easily. They estimated the mean by adding the minimum and the maximum value and dividing these by 2. This shows that they can identify the mean and the median as central tendency measures, but they are not yet familiar with the fact that mean and median were only going to be similar to each other under certain specific distributions, and not all distributions. Isabel and Marcos identified the minimum and the maximum value, and they wrote that more seahorses had a length between 30 and 40 millimeters. So here, without calculations or any other statistical tools, these values give only minimal information. Yet students at the stage are not completely aware of this. Task 3 was to build plots and relate to them. So Alexis and Iram focused on the box plot and used the hint to adequately describe the graph. They identified points outside the diagram as outliers and describe them as data that do not belong to the graph. Note here that there is no criteria as to what it means not to be, that this type of exercise will allow questions as how different must the value be from the rest, in order to be able to say that it doesn't belong to a certain group? Is it just the size of the difference that one should take into account? Or is it also the frequency of occurrence of this value? What information do the histogram and the box plot give that are not provided by something like a dot chart, for example? With task 4 and 5, we worked on further representations of the histogram. And here both teams correctly identified the red line to represent the mean. Isabel and Marcos also added a median as a blue line and discussed its similarity to the mean. But then they typed the following code without any reflection. So they produced a yellow line, 2 yellow lines for the range, one for the minimum value and the maximum value. Can't see it very well because it's very light. So there's a yellow line over here for the minimum value and for the maximum value. And they also produced a green light for the standard deviation. But they did not realize that the green line was completely meaningless in a single x dimension, like the one represented here. Isabel and Marcos failed to perceive that one could roughly estimate the size of the sample just from looking at the histogram. But Alexis and Miriam could sort of realize that if they added the bars, they would get to some kind of rough estimation of the 100 observations that made the sample. So they know that some equations can be calculated, and they show ways of calculating measures instead of using the direct functions in R, but they typically concentrate very much on the operative aspects in coding rather than the interpretation of what these measures mean. In task 6 and 7, they started to investigate randomness and sample size, and Alexis and Miriam answered by simply answering the code, analyzing the code rather than trying it out. And they said that that this code would output a sequence of random data with an argument for having 100 elements. They used modularity to change the value of 100 and repeatedly created different samples and compared their means. And then Miriam said that he believed that the sample mean would get closer to the true mean as n gets larger. And in his logic, it followed that samples with a small n would produce values that would be very different from the true mean. So they are certainly very struck when a sample with n equaling 2 had a mean of 29.7, which is very near 30, and they think that they have made a mistake. I asked whether it would be possible to obtain a mean value of exactly 30 by collecting a sample of only one observation. And they turn to look to the list very quickly. When they find the data point with a value of exactly 30, Iram says, it is possible. We can have a mean value of 30 with a really small n, because it is random. It may have a very little probability, but it can happen. But, however, it has a very personal experience to what randomness means. So, in general, after 14 courses and almost 4 years of work, we think that we have results indicating qualitative data and anecdotal data that point out to, in general, strong positive effects of these activities. We believe we have increased the self-appreciation of the students. We believe that they have overcome some of the mathophobia that they presented at the beginning of the courses. They are much more autonomous in the use of statistical and technological tools, and they have a larger or increased creativity in the use of many of these tools. In terms of the appreciation of the course's approach, we have evidence of an increment in attendance to the course. In 2013, we had a course of maybe 14 students, and 14 students in 2013, compared to 27 students in 2016. And we have comments like the following. When we correct the activities all together using the beamer, I think about my mistakes and I won't make them again. That is said by a student of an undergrad course. They like becoming aware of the different ways in which you can arrive to a solution to the problem and the use of different tools to achieve this. Another student said, I like that you believe in us. You believe you can learn, and that really motivated me, because I know I am slow in learning. And even though it is difficult, I try hard. I discovered that I can learn maths, or at least stats. And that makes me feel very happy. She's an undergrad student that had difficulty at the beginning of the course, and by the end was much more inclined to participate, correcting her colleagues when they made mistakes. Also, we have other evidences of changes in attitude towards the learning of statistics. Most students seem able to overcome their initial fears and difficulties of computer programming. They have a deeper understanding of the rationale behind most statistical procedures, and they handle variability in a much more autonomous way, and they are self-confident about it. Stats suddenly has lost its supposed unreachability, and this is not only for specialists, and suddenly it has become a universal tool that can be used and applied in efficient and useful ways to solve their problems, particular and very real problems. And students often become more dedicated, desiring to learn a wider variety of quantitative tools. Misha here, for example, is an undergrad student that approached me recently to say that she had attempted R coding by herself in order to follow a multivariate course that was being taught by another teacher using a window package. She was not understanding anything. So she decided to try herself her R coding and see if that way she could understand what the teacher was saying in the multivariate course. So they feel that R would be a vehicle towards the understanding, or an easier understanding of the stats. Other examples of appropriation are that many students feel capable of using R on their own data, either creating new scripts or modifying pre-programmed scripts, like Jose from Honduras. He said, I am infected with R, and now I only want to use R. He explained that he had been compelled to use multivariate techniques on his data and had investigated on his own commands dealing with these techniques. He had then written his own scripts to analyze his data, and he was very excited to do this by himself. Students are inclined to use more sophisticated procedures that allow adequate and more powerful sampling designs, like Ephraim. He has been using a generalized linear modeling with Poisson regression, which is a very sophisticated and complex procedure to analyze his master thesis. Another student, Snati, emailed me and said, I just wanted to thank you for your course. I am here at a US university, not feeling completely lost in stats, and I have been working on my data using R. I am delivering results and I feel very happy and very grateful. Fernanda, just very recently, also told me, I've done my first dendrogram, and I did it all on my own. And she also said, as soon as I finish my PCA, I will send it to you. Why would I do that, she says in the email. She says, I suppose it's like a kindergarten student that will give her teacher the lovely picture that she has just made. So they feel like children to a certain extent. We all feel like children as well. So as general and overall results, we think the students are active in using and expressing statistical ideas and concepts through our programming tasks. They have generated multiple representations and applications of statistical concepts through formal descriptions in the proper code. Programming was engaging and turned analysis into experience, allowing a connection between analytic forms and their experiential implications. And the collaborative work has served as another means of expressing and clarifying concepts that they have studied. And they have learned the importance of a graph to synthesize information. So,
So we have 3 or 4 minutes for questions.
Thank you for everyone to understand. So I was wondering, because of also a comment that Anna made at the beginning in relation to the presentation this morning, do you see if there could be a way through this study to talk about the kind of understanding that students developed about randomness or probability through doing that kind of activities where it's embedded.
Is there a way as
Or randomness.
well, I suppose that to a certain extent their understanding is very intuitive. So they are. But I think that what is happening is that they know maybe definitions, but they don't understand the definitions unless they actually produce conflicts, such as the one that I have tried to show here. And once they are confronted with this conflict, suddenly they understand what randomness means and how a random procedure can produce something that is very accurate or as well as something that is not so good. And this notion is something that is very much produced as something that they are doing at the moment and while they are doing it. So I believe that they understand what randomness means in the sense that they are actually producing a random number through coding, and it's their coding, so they are writing it, and they know what's happening. So they know that-
We have that wrong question. We hear it.
Now that was weird.
That happened yesterday.
So yes, I think that's a kind of knowledge that they are or understanding that they are. I don't know if I answered you.
Thank you. I think it's very interesting to see how it becomes something that they actually get work with and feel when they just experience randomness with through games or something like that. Yeah.
I think that games also work as two disadvantages. The first is that it's maybe not as quick as enough. Here it is very quick. Yeah? You just have to type and click, and suddenly you have the answer. And you can produce a graph very quickly as well. So you don't need to go to another part of the program to produce a graph. You just have the graph immediately. And I think that quick result.
Poke them and listen to one another.
Well, thank you.
I can go like this.
Yesterday about trying to quantify, evaluate outcomes, and it would be so nice to be able to go a little bit further than the anecdotal.
Yeah, we've been working on this for a couple of years, just more, going beyond that. We didn't do, because Maite and Marta are, they are hardcore scientists, so
We
at
want to
first
quantify
they wanted to do everything statistical, and they actually got a surprise in Lisbon when we went to the statistics education conference there last summer, where everything was qualitative and not quantitative, because especially Marta was saying, everything should be statistical data, and they tried, but it's very hard. Again, we face that problem of what do tests actually measure? Because we took out the slide, but there was a mild improvement in test scores compared to other courses, previous courses, the same course but taught traditionally. There is a mild improvement.
On the same students.
Yes.
We had the same students having the course traditionally, and then they failed the course, and then they got into a second course that was taught using the R program. So we had these two students as just like suddenly, and we could compare. There was a mild improvement, but we could not tell if the mild improvement was just because they had taken the course for a second time, or if it was actually the R programming features that they understand.
And there was also trying to compare scores of tests, not just with these students, but overall of the entire courses. But again, what do those tests actually measure? How are they done? And that's a problem we're always facing. That's what we were discussing yesterday during the workshop. So assessment. So now we're trying to do another type of research where we're looking at the appropriation of the tool and of the concepts by looking, for instance, at the students' dissertations and things like that. But we are developing that. So
up to now, we just have like anecdotal information. Like some of the students have. I know that they are still using some of the activities because they keep coding. So they use these activities and then they take some bits of these programs and these coding, and they use it to do their own analysis. I know they do that because they've come to me, they show me. To what extent that is actually further used, we don't know.
It'd be really nice to be able to set up a series of indicators out of the series of reports and pieces are coming out.
Quick, okay. Dave's got one last question. Try to-
I just wondered whether, so you talked about the advantage, possible advantage that it's quick, compressible, and it gives you the answer. So I'm thinking about the quickness of how a sample is produced, and wonder whether students at any time articulated their ideas about what was happening when the sample was produced. You know, what metaphors or images did they have of how the sample was produced by the computer? Was that expressed in any way?
Yes, it was in a retrospective way. Once they actually saw the numbers and they saw this contradiction with an n equaling 2 and 29.7, at that exact moment I think that they said, oh, what happened? And then came the images of what they were actually doing.
And what sort of image was expressed?
It was, I think that it wasn't expressed directly, but when I asked them, can you find a single value that is equal to 30? Do you think that you could get a single value equal to 30? And they looked it up. I think that in order to go and look it up and then come with an answer, they had to produce these images in their heads. They had to go through the actual process. Okay, so what we're doing is putting our hand in, taking out 2 observations or 3. They didn't say it in that way. They didn't express it in that way. But I think that that would be necessary for them to come with an answer, the answer that they came with. In order for them to go and look for the data in the list, they had to think how they would get a sample with n equaling 2 or 30.
Well, thanks again.